We finished the calculation of reinforcement in the x direction, reinforcement in the y direction, and also done the calculation for finding the depth of the slab, and we also done the deflection check. So now we have going to do one more check, which is transverse shears, whether we require the fitments or not. So first of all, we're going to calculate the design shear force. We done this similar calculation in a one-way slab, so I've just quickly described the same scenario here. Now first of all, we need to calculate a design shear force. In the page number 96 on clause 6.10.2.4, it has given design shear force equations. Now we are working in the end span, so if I show it to you here the drawing, we are working on the end span, and on the end spans at the face of interior support. So at this face interior support, we have maximum shear here. So if you do the shear force diagram, you will have a maximum shear here. So that maximum shear can be found by 1.15 FD ln over 2. So 1.15 FD we calculated in the previous video. I can show it to you. In the previous video, we calculated this factored load 9.6 kilonewton per meter. So that I substitute 9.6 kilonewton per meter times by the 5 meters. So if you are looking that figure again, we have the slab. Ln is the clear distance between the face to the next face. So we will have 550, 250, take away 250 because center to center distance, and beam width is 500 millimeters. So this clear distance is 5 meters. So I substitute 5 divided by 2 is give me around 27.6, which is 28 kilonewton. Now we need to make sure that we need to make sure that whether we want to provide the shear reinforcement or not. So the equations that's given here saying that if your design shear force is greater than 5 VUC, then you require the shear force. Otherwise, you require the fitments. Otherwise, you don't require the fitments. So now to calculate the concrete capacity of the concrete shear capacity, we have an equations given in clause 8.2.4.1 on page number 117, where we can see that these equations kV, BV, dV, square root FC dash. kV 0.15. if you just turn the one more page here, they have give you this kV. Now we are making the assumption that ASV is equal to the fitment, the area of the fitment is greater than the minimum fitment requirement, and there is an equations. If you check the shear video, there is a equation for that. So we just say that kV equal to 0.15. it's just a very crude assumptions, but anyway we're going to check it and let's see whether it's going to come close to this value. If it's not, then this assumption should be far valid than far valid for the calculation. So BV, I think we are taking 1 meter wide strip, so we are taking 1000 millimeter width of the slab. DV is the effective depth for the shear. So if you just turn the page over in the clause number 8, clause 8.2.1.9, you will find this equation 0.72 times 0.9 D. Now depth of the slab 190 millimeters, we found that in the previous video. Now we have two D's. If you remember that in our calculations we found the two different D values. Okay, I will show it to you here. If you remember that we have 2D, 119 in the dx and 107 in the dy. Well, for the conservatives, we will take 119 because these parameters will not going to control the maximum dV. It will going to control by this one. So regardless, we will just use for conservative, we will use maximum value here. Instead of 107, we can use 119. So here we will have a 0.9 times 119 give me 107, and maximum would be 137. So if I substitute all the value, 0.15 here, 1000 here, 137 dV times square root 32. I think in the questions it has given us this concrete compressive strength 32 megapascals, concrete compressive strength given in the question. Substitute here, it gives me 116 kilonewtons. Capacity factor 5.75, I think given in table 2.2. If you go back to the front of the standards, you will have this table 2.2.2 where it has given 0.75 for the class and fitments. We just, let's say we are using class and fitments, we assume that we will provide class and fitments if we require, then we will use 0.75. so that is 0.75 here. If you compare these values, which is the 5 VUC, which is 0.15 times 116 as we just found, it is 87. Now 87 kilonewton is far greater than this 28 kilonewton, meaning that all the reinforcement will be taken by this this concrete, so we no need to provide the fitment for the slab. In the next videos, next two videos we will finalize these examples. Thank you.